being talked here, and I'm all very grateful to the audience for patience, and it's the last talk, so thanks for surviving till longer. Just like Nikita, I'll list some of my colleagues. So, the work I'll be describing is based on some published work and work in progress, and the people Gibson, my student Austin, postdoc Walter Collins. Let's see. So Nikita, well, and somebody else. So I want to start with a problem that has been discussed to some extent here, namely quantization of Partition moduli space, all denoted by MH, G, C. C is a Riemann surface, and G is a compact Lie group, as has been mentioned in a number of talks. This is an interesting problem, and MH itself is a very nice, beautiful space. It means hypercalorimetric. And much of this structure, namely hypercalorimetric structure, does depend on the choice of complex structure on the Riemann surface C. However, there is a little bit, in particular one of the complex structures, which doesn't require choice of complex structure on C. And with respect to that, this moduli space is in fact moduli space of flat GC connections on the Riemann surface C. So this particular choice inherits complex structure from complex structure on that group. So quantization of this phase space leads to a Hilbert space, which is very interesting, but not only to the Hilbert space, also it comes with a lot of additional structure which can be packaged in the gadget of three-dimensional TQFT. In fact, in this case, three-dimensional TQFT in question is a familiar type of Chern-Simons gauge theory. So I'm sure Jim would love it. Based on a complex group GC. So the complex gauge group GC appears as the gauge group of this theory. So this is a very interesting gadget in itself. So let me tell you a little bit of the structure of this theory. In particular, what's going to be relevant for the rest of the talk.
Do you literally mean Hilbert space? Or just
I'm not going to use Hermitian in the product, if that's what they're asking. And it plays an important role, but in this talk is more like a survey, so I'll try to explain simple points and hide a lot of technical, interesting details, which are good and interesting, but I simply won't get to. So, three-dimensional TQFT, whether it's based on real group, complex group, or anything like that, in general is a functor which associates to a three-manifold, and let me call three-manifold M, some number, namely partition function Z, and it depends on parameter, which is often denoted either by Q or H bar. They're closely related. In fact, Q is exponential of 2 pi I times H bar. And of course, it depends on the choice of the three-manifold and possibly additional data, which I'm suppressing in this notation. So, to a two-manifold, such as surface C, it associates a Hilbert space H, which is the point that we started with, and so on and so forth. So to one manifold, namely circle or disjoint union of circles, it would associate a category. To a point, it would associate a two-category, but at the moment, for purposes of this talk, we'll stay at this level and won't go to those complexities of homologic problem. So in particular, I want to focus my attention for now on this object Z, which is, in the case of Chern-Simons theory based on a compact group G, would be a familiar quantum group invariant or RTW invariant of a three-manifold M. So we want to consider its analog, which comes out of quantization of the Hitchin moduli space and has its life in the world of complex group. So this invariant Z has the following form. So first of all, as physicists, we would probably define this invariant Z of M. Now, I'm making kind of explicit as part of the notation as as integral over all gauge connections or equivalence classes of gauge connections of exponential minus 1 over h bar, and then integral of the Chern-Simons form of A over the three-manifold. And this is infinite dimensional integral. So then there are various techniques how to get concrete numbers out of this infinite dimensional integral. And if you're interested, for instance, in a saddle point approximation in the vicinity of some flat connection A, then the result you get is of the form exponential of minus 1 over h4 as 0 plus Taylor series, which sums up all possible corrections in h4, so sum over n, h4 to the n. This is the kind of answer that you get by expanding this integral around the saddle point. So,
You don't have the sum of the saddle points?
no. And
Are you going to assume it's isolated, the saddle point?
They often come in families, so in fact, there are various parameters that I should probably add as part of the notation. So this partition function will depend on several things. So it will depend on the choice of three-manifold, A4, and various parameters, which include choice of the flat connection, that is classical solution around which we're expanding, and in fact it's natural to consider three manifolds with boundary. In that case, there will be additional parameters which label boundary conditions. So, because I won't have time to go into detail in this talk, I'll lump all of them in single word parameters, which will be various arguments in this talk. Okay. Now,
Is there a refinement of this abstract nonsense thing that we should use parameters?
Oh, yes. So this abstract nonsense is also a function of the same data. I'm just trying to make it more explicit. So it does depend on parameters. All of this stuff. So this partition function is a very concrete expression, and I want you to remember its schematic form, dependence on h4. This is the only crucial point that you have to remember about this complex Chern-Simons theory for the rest of my talk. And now I want to make, without going further into detail of this theory, I want to make a few remarks motivating why it's interesting. One comment I want to make is because the phase space we're quantizing, namely the Hitchin moduli space, is non-compact, the Hilbert space of this theory is infinite dimensional, and this is a root of many intricate and interesting parts of the story that complex Chern-Simons theory hides compared to that based on a complex group. So that is one particular important aspect which is important. Another remark I want to make is that in this perturbative expansion, or more generally, whether you treat it non-perturbatively or as a perturbative Taylor series expansion around a classical solution, h bar is just a complex number. So for a complex group or GC Chern-Simons theory, H bar, roughly speaking, is just a complex parameter. In fact, it doesn't even have to be real. And for analogous Lie theory based on a compact Lie group G, as you probably know, H bar is 1 over integer. Integer is usually called K and is the level. This is another general aspect of this story that I want you to keep in mind.
So no quantization even though GC has a compact set?
Yeah, there is a quantization, but for, again, zero level approximation to the stock, you can...
If you're just working perturbatively, then I understand.
Yeah.
Okay.
So, and yet, even non-perturbatively, there is a quantization, but still it's continuous versus discrete. So that's very important because if you ask, for example, the following question, given a power series, Fourier series Z of Q, you could ask, what happens if I think of Q as a variable in, say, modular forms, and try to make an S transformation. So then writing Q as 2 pi I over tau, and making transformation tau goes to say -1 over tau. In a theory with complex group, because tau is 1 over the level, 1 over the integer, this transformation wouldn't even make sense. You would immediately go to Q equals 1, so not so interesting. So you can't really ask this question. But in the analytically continued version of Transheimer's theory, where group is complex and H bar is analytically continued to complex values, you can ask this question. And therefore, if there is any version of hidden SL to Z symmetry or S duality in Transheimer's theory, complex theory is the right context to ask this question. So this is just one of the interesting aspects that would motivate its study.
What about ways of convergence in the series?
Of course. No, to be honest, it's a very delicate question, and it leads to beautiful theory of so-called quantum modular forms, which are as far from nice modular objects as humanly possible. So this is really nice, interesting story, but yeah, I'm just mentioning with a broad brush some aspects that I hope everyone can take away without going into too deep level of the detail.
Sergei, while you were reviewing this thing, so in the compact case, the level, the mathematicians like to think of the level as, for a general compact group, any compact group, disconnected, could even be finite and so on. The level is an element of H4 of BG. Is there a similar statement for complexified groups?
To be honest, I don't know useful. Yeah, I have thought about it a lot, and I'll be happy to discuss it afterwards. I don't know. There is a naive generalization of that statement, but I don't know useful analog. I mean, it seems that it's related to algebraic K2 of C, but and that story will have its own phase in this context that I mentioned, but I don't know. So the honest answer, I don't know.
But is this actually that exists?
Good. So, right, this object is very concrete, and as many of you in this audience like explicit concrete formulas that can be written with coefficients, there are many examples in which you can compute these numbers Sn, coefficients in this expansion, very concretely. And therefore assemble them into this formal power series in H bar. Let me just briefly sketch one of the ways. Suppose 3-manifold M has triangulation, so you can write it as union over tetrahedron delta I. Okay.
No boundary?
M may have a boundary. I mean, suppose you take an ideal triangulation of such a 3-manifold, then one of the ways to compute this object is by finite dimensional integral, which in some sense is a mini superspace approximation to this infinite dimensional integral. and this guy z of h bar and m can be written as integral over product of quantum bilogarithm functions phi h bar I. So index I runs here over triangulation. So we're taking product over this tetrahedron in triangulation of n. And to every tetrahedron, you associate a quantum bilogarithm function, which was already defined in various talks, and you integrate over finitely many variables zi. For instance, if your manifold admits triangulation into two ideal tetrahedra, for instance,
You talking about the SL2C?
yeah. So for now, I'm actually thinking about SL2C. That's right. So that's a good point. So let me specialize even further. Take GC to use SL2C, but there should be an analogous mini superspace for GLNC.
When you write the z, so the zi is sort of commuting variables?
Yeah, everything is commuting. So here,
Okay,
this is real,
actual
non-literal,
functions.
everything is concrete. This is very, very explicit.
From dependence on boundaries, where it is.
And dependence on parameters is in parameters of this quantum bilogarithm function. So as I say, this depends on parameters, which encode choice of classical solution, flat connection. And when you write quantum bilogarithm, this function phi bar, it also has place for many parameters which are hidden here. So I'm not going to describe this in detail.
Which contours?
And some contours which, for the various details of this expression, I refer to paper with Don Zagier and those other people I mentioned. So in more detail, you can get this formula not in a schematic form the way I'm writing it, but rather in a very concrete and detailed.
Does it? Is this is a convergent integral or just a formal power series in H bar?
So far, just the formal power series in H bar, exponential of formal power series.
So this produces the sort of exponential of 1 over h bar s naught plus.
Exactly.
Okay, so you
And
can
this
use
is actually all I need. I don't want to go non-perturbative. I really emphasize on, I want to really stick to the perturbative expansion exactly.
Okay, then contours don't matter, or almost don't matter.
You mean matter to transimus theory?
No, then the choice of contours doesn't really matter. Right?
No, it does. It does. Actually, right. So there are many.
Okay. So
There are many details in the story, and choice of contours does matter. It also depends on parameters, but it's not going to matter for my talk. All right. So I want to focus my attention on this function z of h bar, which has this general form and some salient properties of this complex transimus theory I just emphasized. Okay. So now I want to switch gears and go to a slightly different system. Namely, t equals 2, n equals 2, H theory. Plus various vector fields. So we'll scan through the space of such theories and we'll vary gauge groups and matter content. But because of two-dimensional 2,2 supersymmetry, you can actually put such theories in omega background, or in other words, put them on R2 H bar instead of the usual two-dimensional space, and suggestively anticipate infinite connection, and using variable H bar instead of epsilon. So this is the theory in the omega H bar background. And you can try to formulate this partition function, which is basic analog of Nikita's partition function on a 4-dimensional unequals 2 gauge theory. And that will be an object which certainly, just like 4-dimensional partition function depends on epsilon 1, epsilon 2, this one will depend on h bar. So how will it depend on h bar?
And this is Samson's Young function.
No.
It's closely related, but no. It's close analog of it. So I'll comment on this. In some sense, anticipating and going a little bit ahead, Samson was considering reduction of a 4-dimensional theory to 2 dimensions, and what I'm doing is going from 2 to 0. But the step is very closely related, so there will be a lot of analogous structures and properties. So in particular, this z of h bar has the following form. It's exponential.
In 0 dimensions, you will have 2 parameters. That's epsilon 1 and 2.
Epsilon b equals 2.
I'm starting just with 2 dimensions.
Yeah, so you have 1 parameter, and this that h is still different from Young function, yeah?
It's going to integrate exponentially.
Right.
Yeah,
It's
exponential.
it's very similar.
Integrate.
The step of reduction from 4 to 2 is very similar to what's happening here. So they were localizing, they were thinking about a 2-dimensional theory. As Nikita said very clearly, you can think of a 2-dimensional theory with a 2-dimensional Poincare invariance, which doesn't have to be 2-dimensional. It may be a reduction of a 4-dimensional theory on what I'm calling here R2H bar. And now I want to do something else. I want to put this 2-dimensional theory itself on R2H bar. So that's my starting point. And it's localizing again, just like in the original Nikita's work, back to 0-dimensional instant points.
So from the 4-dimensional point of view, you have you have an omega epsilon background with 2.
He did not come from 4 dimensions.
No, I didn't come from 4 dimensions. So the starting
But
point
you
is
could've.
already 2-dimensional.
Could have.
Good have.
Okay.
But in particular, there are many theories in 2 dimensions which don't come from 4 dimensions. That's the starting point. In fact, I'll consider an example for you later today if I have it. So, on general grounds, and this is similar now, this is close to what Samson was explaining, this partition function, which I'll call vortex partition function, in 2-dimensional context is counting instant ones, but instant ones are really vortices. So, again, we talk about gauge theory, so that's at least part of the title of my talk. And this vortex partition function will have a general form. I call it 1 over h bar times some nice smooth function which depends on parameters, plus the Taylor series expansion in h bar which encodes further equivariant corrections. So the reason for this general form is of course very simple, that again this partition function in omega background is defined as, so to say, regularized version of the path integral of the supersymmetric theory on R2H bar, and because in this equivariant signs, volume of R2H bar is 1 over H bar, the classical term is basically coming multiplied by the volume. It's expansive, and therefore that's the most singular term compared to 1 over epsilon 1, epsilon 2, term which is roughly volume of R4, super volume of the 4-dimensional. So I hope now you notice similar form of this H bar dependence to perturbative expansion in another theory in the very beginning of my talk. So wouldn't it be nice if, given a free-manifold M, you can formulate some effective two-dimensional n equals 2.2 supersymmetric gauge theory such that the vortex of this two-dimensional effective field theory as a function of H bar reproduces that perturbative expansion in the transaminase theory on a free manifold F.
But your gauge group here is not complexified on the two-dimensional.
No, it's not. It's not.
There.
Right. So, before we go any further, I want to get you in the right mindset for this. And yeah.
Network, you don't actually talk about gauge. It's not W theory. Is this W with exponential or the other exponential? There are two kinds of formula diagrams. Is this W or W tilde?
This is W tilde because it's
Sorry, what's W tilde then? Be a little more.
The twisted superpotential.
it's a twisted superpotential. So
Super potential for the
I'm asking because there is a trivial way of mapping Chern-Simons theory to two-dimensional Landau-Gizmo theory, where it will be superpotential. And you can also turn on negative ground with D1.
That's what given time did?
That's what essentially. What Gimdal did was in mathematical language, so you can't tell, but it was superpotential or superpotential.
well, I don't know actually such a statement on either A side or B side because this is data. So see, the data of the effective field is encoding topology of the free manifold F. So I know of no statement, at least so far in the literature, that should tell me how to write Landau-Ginzburg model given, say, figure-8 Mach complement such that the omega background reproduces the partition function of Chern-Simons.
Take the space of chiral fields, the complex gauge fields, yeah? The superpotential is the complex function Simons. And you have to know the medial ground in the D1. Exponential. The partition function of the medial ground in two dimensions is exponential integral. For superpotential, it's exponential function. That exactly.
Okay, then I think it's closely related to what I'm going to say. But
Is that an A model or a B model?
He's not specifying that. I'm not allowed to ask.
Right. No, that's a good point. So I'll try to come back to it, and again, I'd love to hear about what Greenthal did because I'm not familiar with it.
No, Greenthal decided it first. Greenthal just, I mean, if you read Greenthal carefully, you can guess what's the definition of omega the ground. So that's.
Oh, in two dimensions. Yeah, but this has been worked out even after him by your student, for instance, in more details in the language that's suitable for what they do. Okay, so I want to take this correspondence and compare it to ADP correspondence, which does something very similar. So it starts with Riemann surface C and aims to reproduce a partition function of a non-supersymmetric field theory on C, a Liouville theory, via omega background of supersymmetric gauge theory. And again, given the topological type of C, you construct some contracted four-dimensional sample to supersymmetric gauge theory such that in this case, any so-called partition function, which depends on epsilon 1, epsilon 2, is the same as Z Liouville or Z conformal field theory, more generally, associated to that Riemann surface C. So one side of this correspondence has to do with supersymmetric gauge theory in a flat space, but omega deformed. The other side, in both cases, has to do with a non-supersymmetric simpler theory on either three manifold or two manifold, and the data of those two and three manifolds are translated in the spectrum of fields in the supersymmetric theory. Okay. So, any questions so far?
So, is the correspondence vertical or you should interchange places? Who is who in the...
Well, you should compare. I mean, this is, you should think about it in a similar way,
So
but correspondence is
You process.
So there was 2 and 3, and now it is 3 and now it is 4 and 2, or
It
was
was 2 and 4 and 3 and 3.
Yeah. So, two-dimensional CFT is encoded in four-dimensional gauge theory, and here three-dimensional transassignments like this will be encoded in two-dimensional supersymmetric theories. And
I would have expected the sum to be 6 in both cases.
well, of course, six-dimensional theory is behind the scene in this case, and now, in order to make this correspondence precise, so far I presented it as a similarity between H-bar expansion in both cases. I want to work out the dictionary for you, and I actually want to explain that it makes sense and where it comes from. So my goal is to appeal to the five-dimensional.
It's natural, just a product in one case, the sum in another.
So, the talk is structured so that if you follow the talk at each step, you should be able to anticipate what the next step is. And of course, the next step, just like in AGT correspondence, though I think to understand this correspondence is to start with the bigger theory, complexify it on C. Here, if you want to understand this correspondence better, we should start with the higher dimensional theory and try to complexify it on M, which is anomaly C. So, luckily, we don't have to appeal to non-existent six-dimensional theories. They may exist, but they're not constructed.
To non-existent five-dimensional.
Yeah, here we have to appeal to usual, in a standard sense, five-dimensional Emil's theory. So take that.
I would say that the 5D theory does not exist and the 6D theory exists.
I should say that five-dimensional theory is six-dimensional.
Right. But at least it exists classically. So five-dimensional maximally supersymmetric Emil's theory,
But actually, it's a serious point. I mean, are you going to use some ultraviolet fixed point in 5 dimensions, or are you just thinking about the
I'm going to regularize it in a very simple way, which you'll see in a second.
Actually, it's not fair what you said, because this five-dimensional theory will be considered in some compact space M, and that one I think exists.
Well,
Columns ultraviolet.
Yeah.
Oh,
Compact fine does not make that.
You need, I mean,
But look, you can always put the 6D theory in a circle kind of thing.
all right.
and that's the right way to think about it. So take a 5D maximally supersymmetric gauge theory on the product of M and R2 H1. So this is our three-manifold, and R2H4 is the space-time of the effective two-dimensional theory, which is supposed to encode its topology and whose vortex partition function is supposed to reproduce transcendence partition function of M, I think. Now, in general, I suggested to take M to be, say, complement of the figure 8 knot or some other interesting three-manifold, and these manifolds are very curved. So in order to put supersymmetric theory on such background and preserve at least some of the supersymmetry, what you want to do is you want to do a partial topological twist of this five-dimensional theory along M. So in fact, it's partially twisted, partial topological twist along M. What kind of twist? Well, five-dimensional gauge theory has a gauge field, a mu, and it has 5 scalar fields, phi I, where I goes from 1 up to 5.
There is a unique twist in five dimensions, so that's the one we should introduce.
Well, if I want to get n equals 2 two-dimensional theory, I don't have to do full twist, right? It suffices to consider only
Yeah,
partial
you get
twist.
more twists.
Right, but it's natural to think about this as a unique twist in 5 dimensions, which complexifies the same. So, spelling out this telegraphic remark, the partial twist that's relevant here is such that 3 out of 5 scalar fields, phi I, produce a one form such that the combination with A becomes complexified gauge field, and in fact, the resulting topological field theory on M has classical solutions which are precisely complexified flat connections. So in this way, you automatically obtain two-dimensional effective field theory on R2, which has the right supersymmetry. If you ask yourself, how many supersymmetries in this process have I lost, you'll discover that you end up with two-dimensional n equals 2, 2 supersymmetry on the remaining part of the space, just as we wanted, just as the doctor ordered. And moreover, this effective theory has classical vacua, which are exactly complexified flat connections on them. So that's a good starting point. And if this is clear, let's try to go further. In fact, it immediately tells you what kind of effective theory. I didn't tell you the rules. AGT had a very nice dictionary how to go from combinatorics of pair of ends decomposition of a Riemann surface C and how to start with this combinatorics and read off the spectrum of the H theory in terms of extended figures. So here there is an analogous procedure, but you don't even have to invent this dictionary in the simplest cases. For instance, if 3-manifold M is a 3-sphere length space, you can immediately read off the answer from what I just told you. You just do the most obvious compactification or topological reduction on M and see what the fields are. This is, of course, only valid and easy in cases where a 3-manifold is simple enough, again, such as 3-sphere length space, where the set of classical solutions is very simple. In general, you have to work harder in order to get to those quantum logarithms that we had in complex transcendence.
So is M compact or not?
M is compact, and I'm thinking about nice compact manifolds of finite volume, but there is a natural generalization to non-compact cusp manifolds such as...
Compactor, compactor finite volume. I mean, the complement of a figure 8 knot.
Yeah, so complement of a figure 8 knot is a natural generalization which I can include in this class of examples, and in fact now I'll go to even wilder examples which are non-compact. So as I said from the beginning, we can consider complex transcendence on non-compact manifolds M, and I'll have examples ranging from nice and really compact manifolds such as 3-sphere to complements of knots which are mildly non-compact to something which is very non-compact, and that's fine.
But if the sum set of is hyperbolic manifold, so your system is fine.
I think the story works even in greater generality, but at this stage, I should probably assume that it's a finite volume. Again,
Where do you see the volume of M?
it doesn't directly appear, so that's why it's kind of a question which, in the end, once much of this is understood, I believe it is not credited so far. Again, it appears as a technical abstraction in some of the calculations, or it simplifies things a little bit. So, but I don't think it's crucial to the conceptual part of the story. So that's why I'd rather suppress. Because again, some of the examples I'm going to describe next will be non-compact. They're not hyperbolic also, but they'll be wildly non-compact at infinity. So you can ask, where have I seen this before? And I promise you that you actually have. You can.
So basically, you are saying that it's easy to compute what is the Higgs branch of this H theory, or it's not the H theory, it's just.
It's the H theory coupled to sigma model, whose target space is the modular space of flat GC connection.
Why do you, so you have reducible connections? Why do you have H theory? If flat connection is irreducible, it should be technical.
Right. If no. Even see if right. So first of all, you do get reducible connections. For example, even on a 3-sphere, again, going back to this baby example, if it's a 3-sphere, then it has only one flat connection. In that case, the other complication of the story does not arise. It does not come in families like in many hyperbolic manifold cases. So there are no parameters, right? But in this case, there is one flat connection. However, it's highly reducible, so it actually does give rise to SUN gauge field in 2 dimensions. So it's pure gauge theory from the 2-dimensional point of view. So there are all these trade-offs. Okay, now we're seeing this, this naturally appears, where does this partial topological twisting happens? It naturally happens if you think about this 5-dimensional theory as a whole volume theory on the D4 brane. So you can think of this whole picture as a theory on the D4 brane. So world volume of the D4 brane is R2 cross M, and D4 brane lives in type 2 string theory, so it's embedded in a 10-dimensional space-time. But in order to be supersymmetric, it has to see inside R4 cross Calabi-Yau, and Calabi-Yau locally in the vicinity of the D4 brane looks like T star of F. Okay. So 3 adjoint fields, which became imaginary part of this complexified gauge connection, are Higgs fields which correspond to the motion of the D4 brane in the directions, in the 3 other directions of the Calabi-Yau space come from here. So effective field theory on the D4 brane gets automatically topologically twisted if M is a Lagrangian submanifold inside Calabi-Yau. And this setup, what it reproduces for you is a 2-dimensional defect in some 4-dimensional field theory obtained by compactifying type 2 strings on a Calabi-Yau field. So here is, by counting supersymmetries, M equals to 4-dimensional supersymmetric theory. It may be gauge theory, not necessarily gauge theory. And this Lagrangian, submanifold Lagrangian D4 brane produces 2-dimensional defect, which sits in this 4-dimensional effective theory. So that connects to the other set of words in my title, namely, such defects are usually called surface hypermeter.
So what would be the H bar for that? Does it come from a string? Can you engineer the H bar like this, or it's just after you put the parameter, after you engineer the theory on the defect? Then
No, it's just string coupling constant.
What? No.
Don't give you multiple choice answer.
Oh, that's good. Yeah, like it. So do you engineer H bar string theory?
Since we're in the US, students, it's actually good to give multiple choice on questions rather than open-ended questions. So I like multiple choices, and the answer is B.
Answer is
yes.
Wait.
Oh, he has to start over then because you forgot what was here.
But honestly, what is
It's a string coupling constant. It's G string.
Sorry.
Or for topological.
topological G?
Yeah. So it's
How do you engineer it?
Why not?
yeah. Or proper thing to do is to actually. Now I'm going to see. I'm giving you a tour through several subjects. So now I started from a 2-dimensional gauge theory which counts via counting vortices. Chern-Simons partition function, then we went to this 5-dimensional theory. Now we think about it as a D4 brane living on a Lagrangian submanifold M in some Calabi-Yau space, and that's the right setup. So I promise you there won't be any further ingredients or dualities involved here. But once you think about type 2 strings on a Calabi-Yau space, you can actually consider BPS partition functions. And these are right generalizations of the topological string partition function because this is allowing us to introduce 2 parameters epsilon 1 epsilon. Again, by essentially same rotation in our function.
No, but I'm very interested about whether you actually engineered just 1 epsilon or 2 epsilon.
2 epsilons is possible, and again, in my story, it was sufficient to have.
It's hard to engineer 2 epsilons and string theory like
So I'm interested in the question. I'm not asking side question. I'm asking whether what he did was as difficult as to engineer 2 epsilons. And I did not get the answer.
Well, in concrete examples, I can engineer for you 2 epsilons, but for the rest of my story, it's actually sufficient to have just one of them. To have epsilon 1 equals minus epsilon 2 equals h1.
So that's what you engineer. Epsilon 1 equals minus epsilon 2. You don't engineer epsilon 2 equals 0.
To connect to transcendence theory, that's all you need.
Oh.
But that's a really interesting story.
I
I
don't
want to
think
focus
it's
on
interesting.
that.
I'm just, so these two-dimensional servers that eventually you get will be like topological strings eventually. We will have them because it will have this parameter. So because you wrote the expansion in h bar, right? So it seems like the expansion in h bar will be like expansion in epsilon 1 minus epsilon. No?
Look, this theory is not true. Does not serial epsilon.
Well, it does. You can also try to rotate the other direction, and it'll correspond to rotating in the R charge. Taking the index with weights which are R charge. So, in fact, this gauge theories, two-dimensional gauge theories that I started with, where I count vortices, there is also a freedom to write Z vortex as a function of epsilon 1, epsilon 2. I just chose not to do it. But it's possible.
From two-dimensional point of view, this the second epsilon goes into the W.
Exactly.
Then it depends on what kind of bulk theory you have, which is
Right.
trying to avoid.
Right.
See, imagine if M has some multiple singularities, so maybe it's Liouville singularities, and you have ratio of space-time.
So, I thought that the second epsilon goes into W, that's correct. But he said that the remaining epsilon is actually photon, epsilon 1 minus epsilon 2, so then
I think he said H bar is very important. That's all.
Yes, that's all I said.
So H bar is still blue.
But I said that in generalizations, which is what we actually going to consider now.
We dare you to give us geometric engineering of platforms, but let's postpone that.
No, he said he knows.
Well, by refined, in 40 cases, for example, refined
No refined
vertex
vertex.
was good.
No refined vertex.
Okay, in that case, I don't want to do 2 epsilons, I agree. But so either I have to use the crutch of refined topological vertex, or if some kind of analysis of it, or I'm happy to stick to just H bar. Because H bar is the prominent letter in this whole talk. It doesn't turn silence. It's a nice letter I like it. So let me say so. The story is already by far complicated just with one. Okay, so now let me focus on this setup a little bit more and again connect it to the other part of the other part of the title, which has to do with surface separator. So here, if you complexify type 2 string on a Calabi-Yau of a suitable geometry, you can engineer various types of 4-dimensional gauge theories with n equals 2 supersymmetry. In those theories, you have a class of operators supported on surfaces. This is what we encountered here by looking at this default range. And there are various descriptions of the surface operators which are very useful. So in some sense, 2-dimensional theory that lived on R2F, H4, is an effective theory on the surface operator. So let me focus on that a little bit more closely and try to understand effective theories on such surface operators which have 2,2 supersymmetry in 2D. There are various ways to describe surface operators, even if you don't appeal to string constructions, just within gauge theory framework in 4 dimensions. One of them, which is perhaps the most powerful, is as singularities for the gauge field, 4-dimensional gauge field. You just pick a surface D. In our case, it's R2, where surface operator is supported, that sits inside ambient 4-dimensional space-time. And you notice that this is of co-dimension 2 in 4 dimensions. So in the transverse dimensions to the surface operator, we can go around it. It's a point in the plane. And the gauge field can undergo monodromy, as you go around that surface in the 4-dimensional space. Put differently, you can simply require that the curvature of the gauge field A has a singularity delta function supported on the surface D with a suitable coefficient, which is usually denoted by parameter alpha. So alpha takes values in the quartile of the gauge group and parameterizes various choices of such surface vector. There is actually two other ways that I'm going to give you, which give a description of surface operators in terms of additional degrees of freedom. On this surface D. So here we introduce surface operator as a kind of singularity by excising the surface from the space-time and prescribing boundary conditions, namely as monodromy conditions. But in physics, we often describe operators by introducing extra degrees of freedom on the support. And here we can introduce various fields which live on the surface D, and that still remains part of the space-time, part of the picture, which couple to the ambient bulk gauge fields. So one way to do it is to introduce its own two-dimensional gauge theory on D. And this is going to be roughly what I call linear signal model language for engineering such surface operators. And there is another picture which is also useful, which is based on nonlinear signal model.
Question.
Yeah.
When it's actually one-dimensional, but not surface, but the line, looks aligned. So I understand that it's like how do you say, proper time, whatever, on the line, its own quantum mechanics. And then it will be similar to this. But is it obvious that when you have surface operators, these two things are same? I mean, the approach B, let's say, is same as approach A?
Yes, you can show this, and it's explained in section 6 of paper.
Okay, let's go with the paper.
But I don't have time to explain it now, so I'll...
So it's the same.
It's the same.
Yes.
It's the same. And the way to go from C to B, sorry, from B to C to A is to, I'll explain it in a second, is to integrate out various fields and see what remains. What's the effect of that in the action for the remaining paths? By the end of the day, once you integrate everything out which leaves on D, you end up with something, some delta function terms for gauge fields.
In the quantum mechanics case, it's actually easy to see that it will be eventually delta function corrections to that equation. But in quantum field, so it sounds very complicated.
Yes, sir.
But answer is yes.
I think somehow it actually was explained in our other directive.
Was it?
So in any case, you have to go and read the
Was it
confession.
We had some surface operators.
Oh, project.
Which were modeled after Kronheimer-Mlofka. So
Exactly. It was
Oh,
Kronheimer and
these are
Mlofka.
I remember.
Exactly these
I
kinds of
remember
values.
now. Okay. Actually, we call them surface operators.
so many things happened in 15 years. Don't just
People get on.
So let me briefly explain to you what was in the paper. Suppose we have gauge theory with gauge group UN. So just pure four-dimensional UN superanimals. Then in this linear signal model language, you can put the following field content on the surface D, additional degrees of freedom, which will do the job. So you can, in one of the examples, you can summarize theory by the following figure diagram. You can have four-dimensional gauge fields, which I'll put in this node of the quiver. It will correspond to UN node, or node labeled by N. And here I'll put two-dimensional gauge field, just a median gauge field, U1, and this is four-dimensional node, this is two-dimensional node. These fields live only on the surface D. And then I'll introduce bifundamental matter fields, also in two dimensions, also into D, which are in representation n, 1. So they are fundamental with respect to un and carry charge +1 with respect to one gauge field into U. Such surface separator has only one parameter.
That's anomalous, right? Is that anomalous? You have complex conjugates or something?
No, actually,
How much supersymmetry do you have?
2,2.
Okay, that can be anomalous, right?
Well, it has anomaly, but in string construction, it naturally comes equipped with additional multiplets of opposite charge.
Yeah.
But for what I'm going to
Exactly.
say,
Yeah.
it's not
Okay.
going to be important. So let me suppress it. So in this two-dimensional theory, because what's important is that it's abelian theory, and these and multiplets will play well. In general, they come from hypers in four-dimensional theory, so they have both choices. Now, there is one parameter of this system which corresponds to the Liouville term in U1 theory, and that's exactly the parameter alpha in this description. In fact, this is surface separator which breaks the gauge group G, which is UN in our case, to the subgroup, which is UN-1 cross U1, and such operators, we call them next to maximal Levy-type, have only one parameter. In this language, it's alpha, describing the singularity. In this language, this is a phi term. Or if you try to integrate out the U1 gauge field, you get to the description C, where you get a linear signal model. In this example, the target space is CPM-1, which is, of course, the same as Taylor quotient of CM1 but it's also the same as G model. So it's a flat manifold, and it has a Keller matrix, so it's a good target space for the signal model. By gauging its UN global symmetries, you can couple it to the gauge field in 4 dimensions, and you end up with the same surface separator. So in this language, parameter alpha is the Keller parameter of the CPM. In this language, it's Liouville term for the U1, and in this language, it's the monodromy of the singularity. This language is much better than the other two because here, for example, it's clear that parameter alpha is periodic. If you take alpha from 0 all the way to 1, it's gauge equivalent to trivial surface separator. It's much less clear in these languages because when they have the Liouville term or the Keller parameter be periodic.
So this field should not be viewed as a coadjutor between the algebra.
Yeah. Okay, good. So let me do this one calculation in this talk, and connected to string constructions of such surface separators. So here we have three-dimensional surface separators, in four-dimensional gauge theory with n equals 2 supersymmetry, and there are two famous string realizations of that gauge theory. One is ring engineering, where you consider system of D4 branes suspended between NS5 branes. In type 2A. Another is so-called geometric engineering, where you compactify type 2 string periodic Liouville threefold of a suitable geometry, and for example, the toric data of a Calabi-Yau threefold, which corresponds to SU2 gauge theory, is given by this. In both cases, you can introduce, so in both cases, you get effective theory with n equals to supersymmetry in 4 dimensions, and you can introduce surface separators as additional graphs.
This is a non-compact toric Calabi-Yau?
Yeah, these are non-compact toric Calabi-Yau, what are sometimes called SUM geometries. This is the usual geometric engineering story, which again, I don't have time to review, but I hope it will go to most of it. So, in this picture, you can introduce the 2 brains, which stick out in some other direction in the brain picture and share 2 dimensions of their wall volume with a 4-dimensional space-time. So they're naturally surfaces. There is actually a duality, or rather chain of dualities, which relates brain engineering and geometric engineering, and if you naively follow that, you quickly conclude that such brains also become brains in the geometric engineering picture. Namely, these are precisely the default brains that we discussed before. So in the toric geometry, they're usually denoted by these dashed lines in the toric diagram. And these are default brains which have wall volume R2 sitting inside 4-dimensional space-time cross M, where M is Lagrangian submanifold in a Calabi-Yau. Special Lagrangian, yes. For supersymmetry in physical theory, there are special Lagrangian. So this is now, I completed the circle and we got back to another subject, another part of this duality chain, which I was advocating earlier. Now, the geometric engineering of the surface separators, just like geometric engineering of gauge theories, allows to compute these vortex partition functions in a very easy, simple way, just like counting BPS states in these Calabi-Yau geometries can reproduce k-theoretic versions of necroset partition. So let me take 5 minutes and give you one example of a concrete nice calculation which you can now generalize to many gauge theories and Grassmannians and Fleck-Bereans. So the calculation that I want to do, again returning to the basic starting point of my talk, is calculation of the vortex partition function in the simplest 2-dimensional gauge theory with n equals to supersymmetry, where vortex counting is non-trivial and is something interesting. So what we want to do is to, as an example, take 2-dimensional n equals 2.2 abelian Higgs model. This is where we start studying vortices from textbook. This is U1 gauge theory. And one charged chiral superfield.
CP01.
Yes. So in the river diagram, which was on the board just before, the high rates, it corresponds to setting n equals 1. Because remember, the target was CP n minus 1. So if I set n equals 1, I get on the 2-dimensional surface D exactly U1 theory coupled to a single charged chiral multiplet. And just for fun of it, let's quickly do vortex counting in this theory. Well, vortices are labeled by magnetic flux, just like instant clouds are labeled by total instant point charge. And in this case, total flux of U1 gauge field for the 3-dimensional space-time surface D is simply an integer, where you need U1 theory. And it's very well known that moduli space of vortices in this abelian Higgs model is simply M. I'm using notation M for the total flux. Symmetric product of the complex plane. So by definition, this is Cm modular symmetric group, and you can think of it as parameterized by position of vortices, and because vortices are indistinguishable, we have to portion out a symmetric group. So, what would be the equivariant character, Q equivariant character of this moduli space and vortices with respect to rotation in two space-time dimensions? Again, if you think about this m copies of C as coordinates positions of vortices, then it's natural to think of this space as space of polynomials of total degree m.
What is Q? Or you're putting on H bar. You're putting this on at H bar.
Right, I'm turning the limited deformation right now. So what is this symmetric product? Let's think about it a little more carefully. This is space of polynomials of total degree m. So I go from 1 up to m, x minus xi. Of course, you can expand it out. So this will be the space of monic polynomials xm plus a1 xm minus 1 plus and so on x with m. So first of all, this way of doing it makes it clear that this symmetric product, because it's a one-dimensional Hilbert scheme, is actually smooth and is nothing but Cm itself. So first of all, it's in this way of writing it, you think about xi is parameterizing the space, and in this way of writing it, you think about coefficients a's being the symmetric polynomials parameterizing that same space. Also, it makes it easy to calculate the corresponding character. So
Are you doing the two-dimensional calculation or three-dimensional?
I'm doing k-variant version. So I'm doing two-dimensional calculation by thinking about k-variant, which is
Doing three-dimensional computation, we are at you on
so. But I want to tell something simple, so something that everybody can remember. And again, this rotation group acts on xi's in the usual way. So U1 Euclidean acts on xi's in the usual way, just rotates them by phase, by the same things for all of them. Again, if you think about xi's as positions of vertices. But it acts on coefficients am, or sorry, al.
You should have the quantum value.
What?
You should have the quantum
I'm getting to it, of course. It acts on al by different phase rotations, namely I times L times theta al, right? Because if you think about a's being symmetric polynomials of x's, that's what you get. And therefore, the moduli space of vortices in this case is the linear vector space of dimension m, such that U1 rotation group in 2 dimensions acts on this space with weight vector 1, 2, and so on up to that. Okay? So therefore, you can easily write the equivariant character so character Q of M vortices in this case is 1 over 1 minus Q and so on up to 1 minus Q to the f. Okay. Now, just like in Microsoft partition function, what do? You define the Z vortex, which was the original main player in my talk in the very beginning, but again, I spared extra time just to show you that it's very concrete. You can compute it using basic textbooks. And it's a function, in this case, of Q, and Q is exponential of H bar as usual. And it's simply a sum over the vortex number M, also known in the literature as monopole number, in particular in the work of Untitled and Rocca. And it's sum over variable x to the n, which keeps track of the total vortex charge, and character, Q character of moduli space of vortices of charge m. So if you plug it in, you get a very nice, beautiful sum, which can also be written as infinite product product of j from 1 to infinity, 1 minus q to the minus j times x. Okay? Also known as half of the quantum logarithm function. It's not the same as...
Wait a second, don't you need to have a q to the m minus 1 over 2?
This function has many
No, in the
transformations.
first sum, don't you need a q to the m minus 1 over 2?
No, you don't.
No?
I can explain, but it's fun to play with this infinite product. Also
You
called
agree?
Q-Pochheimer
I
series.
think you need...
It has many identities, and it's a lot of fun to work with that, but I'll convince you about
If
this.
you set Q to universe.
Exactly. You use some inverses, and it has lots of good identities. I will be glad to work you through this after I finish. But what I want to say is that this gives a very good example of calculation where this vortex partition function is a partition function of open BPS states on a certain Calabi-Yau geometry. In fact, Calabi-Yau geometry, which is relevant to the surface operator in case with n equals 1, and that's U1 four-dimensional gauge theory, that could be engineered by putting type phase string theory on a conifold. This is the toric diagram of a conifold. If you introduce a single Lagrangian default brane, that's exactly the BPS partition function for the states, and therefore it's example of a much more general statement, like I want to make, that these vortex partition functions are not only related to Chern-Simons theory on a manifold M, which sits as Lagrangian part of the Calabi-Yau, but in some cases, especially when you have the toric toric machinery, you calculate it as open partition functions of BPS.
Any questions?
What BPS states are you talking about? You're talking about type 2 on this
Right.
non-compact Calabi-Yau.
Right.
Just what BPS states are you counting?
D2 branes ending on the D4 branes. D4 brane is a Lagrangian brane whose geometry is, as always, R2 plus special Lagrangian submanifold M, three-manifold M. And in this case, there are D2 branes which end on this guy. Again, this is a simple case which everyone who works on enumerative invariants of Calabi-Yaus would immediately get from Schur functions and refined topological groups. Well, this is of course just a product of Schur functions.
Other questions? Let's thank the speaker again.
Let's thank the organizers.
On behalf of the organizers, let's thank all the participants who came from different places, from very far, and from the 6th floor, from most of the Thank you very much for coming to the presentation.